All right, let's go ahead and get started. Today we're doing chapter 9. That's the gas laws. And on Wednesday we will do lab number 10, water of hydration and potassium alum. Now, this is our last lab, so we should celebrate. All right, enough celebration. Let's talk a little bit about crystal hydrates. When ionic compounds crystallize from water, quite often they can contain waters of hydration. That's not real surprising. We talked a lot about how water can really bind tightly to ions and stuff like that. This is a crystal of potassium alum. Potassium alum, 1 potassium, 1 aluminum, 2 sulfates, and anywhere from, I think 8 or 9 waters up to 24, depending upon exactly how it is crystallized. 12 and 24 are the numbers. This is the 12 hydrate. Kind of a bad image, but nonetheless it'll work. Here's the potassium, here's the aluminum, and we have 2 sulfates right here. These are all surrounded by a shell of water, 12 of them all total, and it makes that very nice little crystal. Now, in this lab, we will get a sample of alum, and the waters of hydration will be somewhere between 12 and 24. Even I'm not sure what they have. So, this is what's going to happen. Crystal hydrates, lots of them. This is a really pretty sort of calcium, uranium, silicon, 5 waters, beautiful crystals, radioactive of course. Nickel nitrate, nickel 2 nitrate, also forms a very nice green hydrate. This is cobalt hydrate. We'll see this again in just a minute. In lab, we have used copper 2 sulfate, which exists as a pentahydrate. And in general, when you have a hydrated crystal, you can drive the water off. Cobalt is an exception in this way, in that it will respond just to humidity. If you take cobalt 2 hexahydrate and put it in a dry space, it will turn into the anhydrous form, which is a lovely blue. You may have seen these. This is actually used as a humidity indicator. Little cards. If it's dampish, it'll turn pink. Once it dries out, it gets nice and blue. In lab, what we did was we took copper 2 sulfate pentahydrate. We heated it in a test tube that drove off the water of hydration and gave us the nondescript white powder, copper sulfate. Interestingly, if you take this anhydrous powder, you can just pour water over it and reform the hydrate right away. It actually gets quite hot as this reaction ensues. So in lab, what you're going to do is you're going to take an alum with an unknown number of waters, and we're going to determine the empirical formula. Now the empirical formula will tell us exactly how many waters are present. We're going to take the hydrated alum, we're going to heat it, get the anhydrous form, weigh it, determine the number of moles of water lost, and get the empirical formula. We're going to start off with a beaker. We're going to weigh it, add the alum hydrate, weigh it again, and calculate the mass of the alum. We're going to heat this, doesn't have to be red hot or anything, just nice and gentle. And we're going to get the anhydrous potassium aluminum sulfate. To get the molar mass of this stuff, you're going to take the mass of the potassium aluminum sulfate, that's what's left after you heat it, divide by its molar mass, and we will get a number. We'll pretend the number is something like 0.016. That's from a couple semesters ago, actual student numbers. Determine the moles of water loss. Well, you know how much beaker plus hydrate was, minus beaker and residue. Again, divide by the molar mass of water, and we get moles. That student got about 0.25. Our empirical formula, we will calculate it like this. Right now, we know this is alum, X, water, Y. Moles of alum anhydrous, moles of water. This is an empirical formula by itself, but you want to actually divide by the lowest value to get a nice integer. So take this, divide by 0.016. This is the same way. This is 15.9, and of course this is 1. So our empirical formula looks like this. We never show the 1, and of course this rounds to 60. Any questions? Nice simple lab, fun to do, and once again, it's our last one. We will continue to meet in D204 every Monday, and we will do other stuff. Another chapter, I think we do exam review in there, maybe even take the exam in there. Wow. So, all right, let's go ahead and do chapter 9, the ideal gas laws. Ideal gas laws. We're going to develop a set of laws that describe the reaction of gases to pressure, to temperature, and to the number of moles. Combine them to make what we call ideal gas laws. This all comes back to our ghostly friend, Avogadro. Let's start with the kinetic molecular theory. We talked about this back in chapter 3. Once again, the kinetic molecular theory suggests that all particles in this universe have intermolecular forces of various forms so that they all attract each other. Example, these are buckyballs, little magnets. It simulates a solid. The magnetism is the attractive force. When you have a solid, the individual particles don't have enough energy to overcome their attractive force, so they just sit there and shake. They can't move. Solid is a lump. If we take the solid and put in enough energy, however, we can start to overcome this. We hit what's called the melting point, and we can convert the solid to a liquid. When we hit the liquid form, these things are still kind of stuck together, but they can slip and slide all over each other. Finally, if we put energy into the liquid, we get to the boiling point, where we convert the thing to a gas. Again, these fly around randomly, lots of space between the individual particles, and note that they are just colliding with the container. lots and lots of energy. So we're talking about gases in this chapter. Gases, hello, there it is. Has an indefinite shape, takes on the shape of the container, continues to fly in a straight line till it hits something. There's lots of space in between them, so you can expand or compress it. And again, gases diffuse uniformly and very, very rapidly throughout their container. All right, when they are in this container, as we saw, they're hitting the wall. They're going fast. They're very light, of course, but nonetheless, they have energy. And every time they hit the wall of the container, they transfer some of that energy. This gives rise to what we call gas pressure. Now, this is actually a calculation. What I did is I put 500 little gas particles in here. The computer then made them go randomly. They're bouncing off these balls, but I left this one mobile. So this is actually held up totally by the energy of collision from these guys on the bottom coming up and hitting it. This is gas pressure. Atmospheric pressure, what we live in, is an incredible 15 pounds per square inch. Now, a square inch isn't that big. 15 pounds is a lot. If we didn't have gas inside of us pushing out with the same force, we would be smashed to death. So, 15 pounds per square inch, that's a lot. To measure gas pressure, we use something called a barometer. Now, these are weather barometers. This is an old-fashioned manometer, it was called. You fill it with mercury through the loop here, connect this to your vacuum line, suck it down, and you can read a pressure right here, pressure differential, fairly accurately. We don't do this anymore. This is all done with electronic pressure sensors, but this is a nice, cute little instrument. They used to have a barometer mounted on the wall. Never worked, so I guess it's gone. But this is what it used to look like. Low pressure storms are associated with low pressure. Hence, if our low barometer here goes down to a low value, that tends to indicate rain. Nice clockwise circulation tends to bring high pressure. High pressure associated with nice temperatures. And of course, that's the in-between. This is an old-fashioned recording barometer. There's a little bellows here. The arm goes and puts an ink line as the pressure goes up and down during the day. Finally, this is my favorite. I grew up in Florida in the 50s, believe it or not. And in the 50s, we didn't have the luxury of something like satellites. Florida also had hurricanes, even in the 50s. That meant that if a hurricane was heading toward you, you had no warning. Basically, not till it got there did you know it was coming. So, life was difficult in those days. And people would have things like this sitting up on a shelf. Now, this is a barometer of some sort. This is sealed with air in it. And this is open to the air here. The way it works is if a big honking storm was coming, low pressure, this would expand, push the liquid out, and it would squirt out the top. So if you were sitting in your living room and suddenly this started to do that, you knew it was time to tape up your windows and take shelter. And it was interesting days.
How does that work? How does that work?
Well, once again, this is sealed, so this is atmospheric pressure. When the pressure drops, this gas expands. As it does, it pushes the liquid down, it pushes it up, and it squirts. Makes a mess, but you know that something bad is about to happen. In lab, we use a mercury barometer. Again, we actually don't really use these for much anymore, but this used to be a very standard general chemistry experiment. Everybody got to make their own barometer. What you did is you took a glass tube, about a yard long. You took a thing of mercury and you carefully filled up your tube. You put your thumb over it, stuck it down in a beaker full of mercury, and let go. The mercury is heavy, it'll drop, form a vacuum, and once the vacuum is formed, it stops. As air pressure increases against the puddle here, this height will go up or down. The height here at sea level, 760 millimeters of mercury. It is defined as atmospheric pressure. Again, at sea level. Now, of course, we can't do this anymore because mercury is now toxic. I guess it always was, but we can't use it in lab at all. But it was so much fun to do. Any questions? All right, units of pressure. I said that the height here was 760 millimeters. That is referred to as 1 atmosphere, 1 ATM. Quite often you will see it simply referenced in terms of numbers of millimeters. Some places, some books use torr, T-O-R-R, instead of millimeters of mercury. And of course, like we saw a bit ago, 14.7 psi, pounds per square inch, but we'll never use that. In the class, we will not use the English measurements. So we're either going to use atmospheres or millimeters of mercury. Now, these two are readily converted. 1 atmosphere is 760. 760 is your magic number. If you want to convert atmospheres to millimeters, just multiply. If you want to convert millimeters to atmosphere, just divide. 760, 1 atmosphere. All right, as we develop the gas laws here, what we're going to do is explore 3 relationships: pressure and volume, temperature and volume, and the number of moles and volume. We'll combine all of these to make the ideal gas law. First comes the pressure-volume relationship. This is referred to generically as Boyle's law. Now, I can promise you I will never ask you what Boyle's law is, but mathematically, of course, you will know what it is. To demonstrate the effect of pressure on volume, we're going to use this little cylinder. This is sealed, has a gauge to measure pressure, and a platform where we can put stuff on it of various masses. Boyle's law tells us that the volume occupied is inversely proportional to the pressure. So basically, the greater the pressure, the smaller the volume. Let's use this. If I take my device and I put a very small mass on it, nothing happened really, did it? But if I increase the pressure by putting a large mass on my platform, as the pressure increases, the volume decreases. That's an inverse proportionality. Now let's do this again without using an equal. What we're going to do here in a very controlled manner is increase the pressure on our piston, and we're going to monitor the pressure with our gauge, and we're going to plot out volume versus pressure. As we do this, volume decreases as pressure increases, but it never goes to zero, does it? Because the gas itself has an inherent volume. So it can't go to zero. Now, this particular curve, it turns out, is a hyperbola. Chemists and mathematicians don't like curved lines, and we always try to find ways to straighten them out. It turns out that with a hyperbola, you can straighten it out simply by plotting, in this case, volume versus 1 over the pressure. If we do that, nice, beautiful, straight line. Again, that confirms it's hyperbolic. So mathematically, Boyle's law, the inverse proportionality, can be written as this. This little sign looks like a Greek alpha, but it's supposed to be slightly different. Stands for proportionality. This says that volume is proportional to 1 over P. That means that describes our straight line here, volume, and 1 over P. Now we're going to do this trick several times today. But whenever you have the proportionality symbol, you can get rid of it simply by putting in an equal sign and a constant. Proportionality can always be replaced with an equal and a constant of some sort. In this case, the constant is actually the slope of the line. It's just a constant. All right, let's take this and apply it to our piston experiment. We know that volume is proportional or equal to a constant multiplied by 1 over P. Let's rearrange that a little bit and say that our constant is equal to pressure times volume. Now, we had 2 states with our piston. One where we had very little pressure, and one where we had lots of pressure. For our first state here, PV is equal to our constant. But this is exactly the same piston, exactly the same gas. So in our final state here with our anvil, our PV is going to be equal to exactly the same constant. It's the same system. So if P1V1 is equal to K, and P2V2 is equal to the same K, that means that these two are equal to each other. Mathematically, this is Boyle's law. P1 V1 equals P2 V2. This is Robert Boyle. He was an Englishman. Doesn't look like a very friendly sort of fellow, but that's just who he is, not being judgmental here. Any questions? Well, let's see how this works in a pressure volume problem. I have 12.5 liters of gas. My pressure is 0.82 atmospheres. I changed the pressure on my piston, so now it's 1.32 atmospheres. What is the volume? Classic Boyle's law problem. What you're going to do is remember P1 V1, P2 V2. Here we're looking for the final volume, that's V2. So we're going to take Boyle's law and simply solve it for V2. V2 is going to be P1 V1 divided by P2. We look at our problem and we substitute. P1 is going to be 0.82. V1 is 12.5. And P2, 1.32. Atmospheres cancel. We're left only with liters for volume. 0.82 multiplied by 12.5 divided by 1.32 gives us 7.8 liters.
What does ATM stand for?
I'm sorry?
What does ATM stand for?
Atmosphere. Automated television. Remember, 1 atmosphere, 760 millimeters. Let's look at another one. Here we have 150 millimeters or milliliters of CO2. Our pressure, 35.3 millimeters of mercury. We are going to change our volume to 50 mils. What's the final pressure? Once again, Boyle's law problem. P1 V1, P2 V2. We're solving for the final pressure, P2. We take our Boyle's law equation. P2 is going to be P1 V1 divided by V2. Our pressure here, 35.3. Our volume, 150. And our final volume, 50. Our milliliters will cancel. And our pressure is 35 multiplied by 150 divided by 50, or 106 millimeters. Now, what if I was not such a nice guy and I said, what is that in atmospheres? Right? Well, if it was 1 atmosphere, this would be 760, right? 760 is our magic number. To get this into atmospheres, you just divide by 760 and you get 0.14 atmospheres.
One atmosphere is 760.
Yep. 760 is our magic number. All right, why don't you take this one and set it up? We have helium. Here's our initial pressure. We're transferring it to a container of 25 liters. Final pressure is 770. What's the initial volume? We're going to take Boyle's law and simply solve for V1. My goodness, it's loud out there. V1 is what we're after. It's going to be P2 V2 divided by P1. P2, 770. V2, 25 liters. P1, 860. Millimeters of mercury cancel. 770 times 25 divided by 860. 22.4 liters.
So if it says initial volume, then we don't need to do, we really don't need to worry about the unit side, like initial volume should always pan out without needing to do extra calculations.
Well, it's not just for the initial volume though. Basically, you want to take your problem and just look and see what are you after. Initial volume, take Boyle's law, and solve for it.
'Cause on the homework, it talks about using like different, oh, never mind. It talks about initial pressure, and that's just going to be
That's it.
Okay, so I'm doing that.
There are 3 tutorials with this chapter. Pressure volume, temperature volume, and ideal gas law. This is the Boyle's law tutorial. Boyle's law tutorial is going to require you to do a couple simple conversions. Sometimes you will be given things in atmospheres. Sometimes you'll be given them in millimeters of mercury. Remember just the 760 thing. Quite often you'll go from milliliters to liters. That's just 1,000. So let's look at this. We have a gas system. Initial pressure is 5.05 atmospheres. Volume of 50 mils. We're changing the volume to 5.6 liters. What is the final pressure? All right. Obviously, we have to change mils to liters or liters to mils, either one. When I do these, I think the easiest way is just to make a list of what you've got. Do your conversions, and then plug it in. P1, 5 atmospheres. V1, 50 mils. We're looking for P2. V2 was given in liters. I could change that to mils, or I could change that to liters. Doesn't matter, as long as they're the same. We are going to rearrange Boyle's law to solve for P2. P2 is P1 V1 over V2. Okay, substitute P1 V1 V2, 4.538, round it to 3 significant figures. Any questions? The ones on Blackboard look just like these. Go ahead and set this one up. Initial pressure 2350 millimeters. Initial volume is 8520. Our pressure is now 5.6 atmospheres. And we're looking for V2. Here's our list. P1, 25 or 2350 millimeters. So for P2, which was given in atmospheres, I multiplied by 760 to get 4260. I could have simply divided this by 760 to get atmospheres. Doesn't matter. This was V1 in milliliters. We want our thing in liters, so I divided by 1,000. V2 is what we're after. This just reminds me to say that. Pressure in atmosphere multiplied by 760. V2 is P1 V1 over P2. P1 V1 P2 3575 milliliters or 3.58 liters. So Boyle's law, pressure, volume, inverse relationship. Greater the pressure, smaller the volume. The next one we're going to do is temperature volume. Temperature volume relationship. We're going to start off with a balloon. This is a fun thing to do. You're going to take a tub of liquid nitrogen, minus 196 centigrade, and dump it on this poor helpless balloon. The balloon will get very cold. We're getting closer. There we are. As the balloon gets cold, that temperature decreases. What happened to the volume? Well, it decreased also. Temperature decreased, volume decreased. It's slowly warming back to room temperature. And when it finally does, the volume increased. Temperature increased, volume increased. That's a direct relationship. We suggest that this will be a direct linear relationship. Once again, temperature increases, volume increases. Same thing with decrease. We predict a simple linear relationship. But as fun as it is to play with liquid nitrogen and balloons, chemists like to do experiments. So what we're going to do is take a container with a known volume, and we're going to change its temperature. And we're going to measure the volume as a function of temperature. We're going to start off with a fixed number of moles of gas in our container. So let's start with 0.25 moles of gas. And sure enough, as we lower the temperature, the volume drops. Let's do it again with half a mole of gas. Again, temperature drops, volume drops. 0.75 moles, same thing. So we feel good, right? Everything is behaving the way it should. But you know, look at this plot. Look at these three lines. They're kind of like all heading in the same direction, aren't they? What if we take and extrapolate these down? When we do that, they all meet at exactly the same spot. Now this is a theoretical point where the volume would drop to zero. We know we can't get there, but if we could, this says that at minus 273.15 degrees, regardless of the amount of gas we had, we're going to be at the same spot. This magic point, minus 273, is defined as zero on the Kelvin temperature scale. Probably better known as absolute zero. That's where absolute zero comes from. Zero on the Kelvin scale. It's a hypothetical point because you can never get there. You can actually get within a few thousandths of a degree, but nonetheless you can't get to zero. This is absolute zero. This is important because the Kelvin scale must be used whenever you do a gas law problem involving temperature. You must use the Kelvin scale. It's actually simple though, because the two are related by this value of minus 273.15. We all know that water freezes at 0 degrees centigrade and it boils at 100, right? In Kelvin, that means that water freezes at 273 and boils at 373. You'll note that there's 100 little degrees in between, the same thing here. So the temperature in centigrade is always less than Kelvin by the factor of 273. Since we measure things in the lab in centigrade, if we want to do a gas law problem, we have to do the conversion. So let's just practice very quickly. If we had 1,000 degrees centigrade, we know that centigrade plus 273 gives us Kelvin. 1,000 plus 273, 1273. If we're at minus 150, we add 273 to that. That would give us 123. And again, if we're at 100, it's simply 373. Kelvin is always larger, and the two are never the same. They always differ by 273. All right, let's take all of this and put it into a mathematical equation. We know that volume was directly proportional to temperature. Volume gets bigger, temperature gets bigger, blah, blah, blah. We know whenever we have a proportionality, we can substitute equal and a constant. And like we did last time, let's solve for our constant. Our constant is going to be V divided by T. This is what is referred to as Charles's law. Now, Charles was the guy's last name. And just like we did with Boyle, here's our balloon that's cold. Here's a balloon that's warm. This K1 is going to be equal to V over T. K2 is going to be V over T, and the two Ks are the same. That means that V1 over T1 must equal V2 over T2, and that is Charles's law. Any questions? How about who was Charles? Well, this was Charles, a Frenchman. Unlike Boyle, he actually looks much friendlier. When I first saw this image many years ago, anybody remember Barry Manilow? I looked at that and I thought, gee, that looks just like Barry Manilow, but it isn't. Okay, this is Charles. Charles was an interesting guy, aside from looking kind of ruddy and disheveled. He was a balloonist, and he had the honor of being the first person to ride across the French countryside in a hydrogen-filled balloon. There he goes. Now, the balloon that he was using, like I said, was filled with hydrogen. Hydrogen was generated by the single replacement reaction, element in a compound, element in a compound, sulfuric acid and iron. The hydrogen is released as hydrogen gas. We get iron 2 sulfate. This reaction also gets extremely hot. So as it came out of his reactor here to fill his balloon, it was really hot hydrogen. And as the balloon filled, well, the hydrogen cooled. What happened? Just like our balloon, it kind of collapsed on itself. That's where we got the idea for Charles's law. How about that? Well, so he filled his balloon, put a little thing on it so he could sit, and went for a ride. Went up as high as 1,800 feet across the French countryside. It must have been very scary. I'm sure he took, he's French, I'm sure he took a case of wine. But nonetheless, flying across the countryside, and decided that, okay, enough's enough. He spotted a small village and decided it would be fun to land by the village. Everybody would come and greet him and say, you know, what a great guy you are, right? Well, unfortunately, the peasants in Greek villages in 1783 were not used to seeing things like balloons flying over, especially with a person getting out. So they did what you would expect. They attacked it with pitchforks and knives. Fortunately, though, they didn't do the other thing that was traditional at the time and attack it with torches, because we all know hydrogen gas is extremely explosive, isn't it? Well, Charles lived through it, believe it or not. And this was his last balloon ride, one and only, but nonetheless, he did live through it. Shortly before World War II, people started using hydrogen to make giant aircraft, blimps, dirigibles they were actually called, and they were filled with hydrogen and they were used a lot. Hydrogen is still explosive, however. The largest of these was made by Germany. It's the Hindenburg. It's absolutely huge airship. It was designed to go transatlantic from Berlin to New Jersey. So they tested around a bit and it worked fine. They went on their maiden voyage. They crossed the Atlantic fine, found New Jersey, but there was a thunderstorm in the area. Now, they held off, didn't want to get hit by lightning. They held off, but probably the outer skin, this metal skin here, developed a significant static charge. And as they finally went in for their landing, they're venting off hydrogen gas, which is explosive. And as they lowered themselves down to the landing tower, it exploded. Big, very classic explosion, lots of people killed. It was a luxury liner for its day, but nobody ever made hydrogen-filled balloons again because they're just too dangerous. It's a shame though. Hydrogen is really cheap, really available. Helium is not, but it does have this nasty habit of exploding. Any questions? Well, let's go ahead and do a gas law problem. We have 50 mils of a gas. We're at 26 degrees centigrade. We heat it until the volume is 62. What was the final temperature? Now, the first thing you want to note is that we measured our temperature in centigrade, didn't we? We must use Kelvin. 26.4 plus 273 gives us, come on, there it is, close to 300 Kelvin. We're going to use Charles's law. We're solving for our final temperature, that's T2. T2 will be V2 T1 over V1. So we look at our problem. V2, 62 mils. T1, 300. V1, 50 mils. We substitute. Milliliters cancel. We're left only with Kelvin. 62 times 300 divided by 50. We're at 373 Kelvin.
How did you get the 299.6 Kelvin again?
We took 26, added 273 to it.
What's 273 from?
273, remember, Kelvin is always larger than centigrade by 273.15 degrees.
Thank you.
Now, what if I was, again, mean and I said, what is this in centigrade?
Subtract.
You would
Well,
simply
you'd be-
subtract 273, right? 101 degrees centigrade. So our second tutorial of the chapter is obviously going to be Charles's Law. Once again, we're going to have to
God
do
bless you.
conversions between milliliters and liters, centigrade and Kelvin, but that's no big deal. We can do that. What I would do again is make a list of what I've got and is do any conversions that I have to do. V1 was given in milliliters. So let's take V2 and put it in milliliters too. Do the opposite, it doesn't matter. T1 was given in centigrade. We add 273 to it, and we get 379. Remember, Kelvin is equal to centigrade plus 273. And we're looking here for T2. That's V2 T1 divided by V1, V2, T1, V1. 264 Kelvin. Initial volume, 0.434 liters. T1 is unknown. Our volume changes to 0.197 liters. The temperature is 209. When we do our calculation, we will get the initial temperature in Kelvin, but the problem wants it in centigrade. So we will take our Kelvin and subtract 273. So, here's what we got. Looking for T1 in centigrade. V1, V2, both in liters. T2 is also in Kelvin. We are rearranging to solve for T1. V1 T2 divided by V2. V1 T2 V2. We get 461 Kelvin as our answer. But again, the problem wants centigrade. What do? We subtract 273. All right, I've got one more here. Why don't you just take this, set it up quickly? We have our initial temperature. Initial volume is unknown. We change the temperature to 164. The volume is this, but we want our initial volume in liters. What I did was take V2, divide by 1,000 to get 5 liters. And again, we know everything here except V1. And these are both in Kelvin, so that's good. V1 going to be V2 T1 divided by T2. V2 T1 T2. Simple math, 13.4 liters.
What would the math be if you do your milliliters to liters at the end? Would you divide your number just by 1,000?
By 1,000, right? All right. That's the temperature-volume relationship. Remember, we got it from our plot here, right? Well, I'll be honest with you, doing an experiment like this takes a long time. It's a lot of work, it really is. And once you do it, you want to try to get out as much information as you can. Okay? So what if we kept our temperature constant and simply looked at the relationship between the number of moles that we added and the volume that we got? As we add more moles, the volume goes up, doesn't it? That's going to give us the mole-volume relationship. We keep the temperature constant and simply change the number of moles. That's kind of intuitive, isn't it? Because the more you put in, the larger the volume should be. We predict this to be a simple relationship, and by George, it is. As the moles go up, so does the volume. This is referred to as Avogadro's law. Very simple thing. Once again, number of moles increases, volume increases, and it's a linear relationship. Okay, so we have Boyle's law, which tells us volume is 1 over P. We have Charles's that tells us that volume is directly proportional to temperature, and Avogadro directly proportional to number of moles. 1 over P, T, and N. Well, mathematically, if volume is proportional to all of these things separately, it's also proportional to these things combined together. That is, volume is going to be proportional to NT over P. Now, we've done this before. We have the proportionality symbol. Let's change that to an equal sign and a constant. But you know what? I'm tired of using K. Instead of using K, I'm going to use an uppercase R. And I'm going to call it the universal gas constant. Now this is kind of neat, because if we knew what R was, if we don't know any of these things, we can simply solve for them. Problem is, what's R? This equation also is not a fun equation. Try saying it. V equals R and T over P. Okay, it's an equation, but it's not a fun equation. If you take and multiply both sides by P, you get this. Much more fun. This is PV equals nRT. It's kind of like lines, doesn't it? This is the ideal gas law. PV equals nRT. The ideal gas law. Only problem is we don't know what R is. But actually we do. This is where Avogadro gets all of his fame, because remember in the mole business? He said that 1 mole of a gas, any gas, at 273 Kelvin at 0 degrees, 1 atmosphere pressure, occupied 22.4 liters. That's everything we need to get R. R is going to be PV over NT. Our pressure, 1 atmosphere, volume 22.4 in 1 mole, T 273 Kelvin. Now, you will note here that nothing cancels. So when you do the math, you get the rather obscure number of 0.082057 liter atmosphere per mole per Kelvin. I can't remember that either. And so if you ever need R in a problem, exam, whatever, I will give it to you. Don't worry about writing it down or remembering it. Well, okay, we know R. That's kind of neat. This means we can use PV equals nRT, and we can solve for any unknown factor. Remember back when we did the piston, right? We had a piston with a little bit of pressure, piston with a lot of pressure. Those were 2 separate states, weren't they? Turns out that the ideal gas laws can be manipulated to come up with a 2-state solution and a 1-state solution. The 2-state. What we're going to do is take this and simply solve for R, which is a constant we know. This is our initial state. When we drop the anvil on it, this was our final state. R is the same for both. Therefore, a 2-state system, P1 V1, N1 T1, P2 V2, N2 T2. This is simply a combination of Boyle's law, Charles's law, and Avogadro's for a two-stage system. Single-stage system. We have our PV equals nRT. We don't know something, but we know everything else. We just simply solve for it. Single state, PV equals nRT. Two state, the more expansive equation. Now, in this class, we are actually only going to do single state problems. Not because these are hard, but they're cumbersome. And people quite often make stupid math errors when they do these problems, and you don't want to miss a question because of a stupid error, do you? No. So we'll save this for general chemistry. But let's just look at a problem anyway. Then we have 0.05 liters. We have a pressure. We have a temperature. We're going to raise our temperature. The volume increases. We have a final pressure of 1.06, and we're looking for the final volume. Okay. Here's our equation. We're looking for V2. We must change this to Kelvin, right? This is V1, T1. Number of moles doesn't change, so we can just forget that. P1, V1, add, excuse me, 273, we get 300 degrees Kelvin. On this side, we don't know V2, but we know P2 and T2. So we multiply this side by 404, divide by 106. Let's see. We are going to cancel atmospheres. We are going to cancel Kelvin and be left with liters. 0.98 times 0.05 times 404 divided by 300 divided by 106. And we're at 0.06 liters. That's a two-state problem. Again, it's not difficult, but it's easy to make a stupid math error, and you don't want to do that. Wait till general chemistry, then make math errors, right? Right. This is a standard one-state problem. We're looking for number of moles. We have a volume, we have a temperature, we have a pressure, and we know R. We're looking for N here. N is going to be PV over RT. Our problem, our pressure, 2.35 atmospheres. Our volume, 18.6 liters. R is going to be 0.082. And our temperature, 293 Kelvin. Atmospheres will cancel. Liters will cancel. Kelvin and per Kelvin cancel. And we're left only with per mole in the denominator, which will come up top, of course. Do our simple math. 1.81 moles. Any questions? We will only do single state problems. And I will give you one. All right, our last tutorial is obviously called PV equals nRT, the ideal gas law. We have volume, moles, and temperature, 5 liters, 0.4 moles, 291 Kelvin. What's the pressure in atmospheres? Looking for pressure, here's volume, number of moles, and temperature. We're simply going to plug it into PV equals nRT and solve for P. That's nRT over V, nRT over V. 1.86 atmospheres. When you do these problems, you have to use atmospheres because atmosphere is one of the units of R. So these are no millimeters, these are all atmosphere.
What, where's your R in the problem?
Yep, right there.
Well, but in the writing, like in the writing portion, where do you state which R is?
I don't know where it is up there, but it's somewhere.
But it does say like R is.
It,
Okay.
R equals something. I hope. Again, if you wanted this in millimeters, you would solve it for atmospheres, multiply by 760, we would have 1408 millimeters. Let's do one more. Go ahead and set this up. We're looking for the temperature, of course, in Kelvin. Our volume must be in liters because R is in liters, isn't it? Our pressure, atmospheres, because R is atmospheres, and everything is Kelvin. All right, we're solving for T. T is equal to PV over nR. P, V, N, and R. Multiply and divide, and we're at 225 K. If you wanted centigrade, subtract 273. Any questions? 3 nice simple tutorials. They all work.
I'm not seeing R listed in.
Yeah?
Yeah, I'm not seeing it.
Okay, it's supposed to be there. Sure.
Check on the-
Catch me on a technicality. 0.0821. Just remember that. All right. Once again, a test question that I thought everybody would get right and nobody did. Which of these are Boyle's law? Well, we remember P1, V1, P2, V2. That's classic Boyle's law, right? How did we get there? We got there because PV was a constant. And if you take this equation and you fiddle with it, by George, you can get this equation. All of these are correct. Again, I thought everybody would get it. Nobody did. Once again, this is Boyle's law by itself. Did Boyle's law because PV was a constant. And if you take this equation and simply divide by P2 and then divide by V1, you get this. Everybody got it wrong. And we're talking 500 people here, and they all got it wrong. So immediately on the next exam, I put this question. It's obviously a good question. Which of these is Charles's law? Well, Charles's law is this, isn't it? T1, V1, T2, V2. No, that sounds a whole lot like Boyle's law. That's not right. And TV wasn't a constant. V over T was a constant. And there is no way in the world you could rearrange this equation to get this one. So none of these were right. On exam 2, I still occasionally put a problem like this with some sort of rearranged equations. So please just make sure you know how to do this. This is a much more standard question. We have a volume, we have a pressure. The volume is reduced, the pressure is 5 atmospheres. The resulting volume is what? Classic Boyle's law. We're looking for the final volume, that's V2. That's P1, V1 over P2. Atmospheres cancel, 90 mils. Here's another favorite question. Too many words again, but when comparing centigrade and Kelvin, what's true? 1 Kelvin is a larger temperature change than 1 centigrade. No, they're the same. Centigrade and Kelvin are never numerically equal. No, they're not actually, because centigrade is add 273 to get Kelvin, right? So that's true. Only centigrade can be converted to Fahrenheit. Well, that's stupid. Any questions? The gas laws are delightfully intuitive. If you simply remember that gas pressure comes about by collisions with the wall. So I have 3 intuitive little clips here. Remember, gas consists of molecules in constant random motion. Collisions with container wall gives us P, and we have no attractive forces.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
If N doubles, P doubles. Makes sense.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
You're hitting the wall harder, temperature goes up, pressure goes up. And finally, volume.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
Volume goes down, pressure goes up. Very intuitive, aren't they? Here's our tutorial list. We have one more in chapter 11. Please make sure you get all these done. April 27th is exam number 2. The final is May 9th. Don't be there for the final. Right? Right. Thank you. Have a good evening, and I will see you for lab number 10, our last lab on Wednesday.
I have to travel to work tomorrow. I have to travel for work tomorrow. Is there anything I can do to make up the lab? I won't be able to make it.
No, I'm sorry.
Okay.
We know we can't.
Okay. Thank you.
Yeah. It's a bummer.
Yeah.